Tonight, the Association of Lunar and Planetary Observers is proud to feature Charles Chuck Wood as our keynote speaker. Chuck is a professional planetary scientist who has long studied the moon, Earth, and other planets and satellites in our solar system. Like many of us, Chuck got into astronomy at an early age. In his case, he was first fascinated by the moon since witnessing an eclipse in the 5th grade. From the beginning of the space age, in the late 50s, he followed American and Russian failures and occasional successes to rise from Earth into space, with the moon as the ultimate destination. Chuck has written 3 books about the moon and is now working on a 4th. His Lunar Photo of the Day, LPOD, website is in its 18th year and now plays daily reruns of ALPOD's, or what I call ALPOD's first 11 years. The Moon Wiki, the-moon.us/ is about 15 years old, and his Sky and Telescope columns started in 1999. Hard to believe that's over 20 years ago. For the last decade, Chuck has been chair of the International Astronomical Union's Task Group for Lunar Nomenclature. His fascination with the moon is renewed every time he observes it with one of his 8 small telescopes. As for his keynote talk this evening, Chuck will describe how basins, the biggest lunar landforms, influence much of what we observe on his favorite telescopic world. As he says, all in all, many amateurs have overlooked basins while searching for small details. Now is the time to see the really big picture. So at this time, I turn it over to Chuck Wood.
Thank you, Ken. Thank everybody for being here. As I look around the folks on the screen, some of you have hair as white as mine. And it may be that your first association with the ALPO was the same as mine. When I was in high school, I wrote a letter to Walter Haas asking him a question about the moon. And he responded on his high school paper, blue-lined paper, right? Answering the question. And I should have kept that. I should have framed it. But it made me realize that there were people out there who were willing to talk and share their knowledge, just like Scott said a few seconds ago. So I've had only small periods of close interaction with the ALPO through my career, but it's always been fun. I hosted I think it was ALPO. I can't actually remember. ALPO and Astronomical League meeting in Tucson in the mid 60s. One of the things I remember about that is that I stepped in the celebratory cake, which happened to have been put on the ground, and I walked right on top of it. So it was a highlight of the meeting, at least for me. Somebody, I don't remember who, said, for such a long time, amateurs did not look at the large features on the moon. They looked to find the smallest ones. And here's a picture of Mare Serenitatis, which is a very prominent mare on the moon, surrounded by mountains on the west and interesting craters around the edges. And the thing that most astronomers who studied the moon from the 1780s through the 1960s, the thing that most of these people looked at, next slide, Ken. Next, can you get it? Trying to.
There you go.
There you go.
It just responds very slow.
Dot over here, which is the crater Linnaeus. And here's a great photo from Jim Phillips, who's got the Valentine dome up in the upper left of that insert. And down at the bottom right, surrounded by bright material, is Linnaeus. Linnaeus is the most famous crater of the 19th century. And as I say there, it's a non-event. What happened? Julius Schmidt, the great Schmidt of Athens, he was called, who made the best map of the moon in the 1900s. he announced in the 1860s that Linnaea, which had been an easy to see 10-kilometer wide crater, disappeared. And there was just this little bright spot that was in its place. And so that was what so many people had been looking for so long. They wanted to find change on the moon. When they looked at the big craters, other than all the little pits on the floor of Plato, most astronomers saw no change. But there was this vast interest in finding and documenting change on the moon. Was there an atmosphere? Was there plant life? And so when the famous astronomer Schmidt discovered this crater that had disappeared, that was a fantastic justification for all the work they did. Next, Ken. Well, that process of looking for change meant you had to map smaller and smaller features. And Percy Wilkins' famous 300-inch map of the moon, I don't know if anybody ever saw the 300-inch. I know that ALPO has something online which says it's the 300-inch map, but I don't know if it really is. But the maps became more and more full of detail. And as you and Whitaker said, the addition of fictitious fine detail is so cluttered Wilkins' map that's virtually uninterpretable. In other words, we looked for changes that were only based on what we had made drawings of. And drawings are amazingly imprecise, even for the best artists, graphic artists. They're imprecise because the moon's look changes every time the sun angle changes, which is constantly. So there was no really documented case that a transient phenomena had really occurred on the moon. Next, Ken. Well, in searching for these tiny changes, what happened was that almost everybody who studied the moon missed the biggest things happening, the biggest things that ever happened in the moon, the impact basins. And when I say everybody who studied the moon, pretty much no professional astronomers studied the moon after Julius Schmidt and a few people before him in the 1800s. And the astronomers who studied the stars and galaxies, they discovered spectroscopy. They discovered ways to find out about everything else in the universe except the solar system. And so the solar system was pretty much left to amateur astronomers. But in 1949, Ralph Baldwin, who died, 10 years ago, 8 years ago, he wrote a book called The Face of the Moon, which was the first modern book about the moon. And he pointed out that what we called Imbrium, which was the lava flow that stretched across this large expanse, and Nectaris, which is the name of the small lava flow in the middle of the picture we're looking at right now, he recognized that those were craters. Those were the biggest craters on the moon. And Bill Hartmann and Gerard Kuiper in 1962 further studied these things, and Bill gave them the name Basins and recognized that they were a totally new type of lunar landform that, other than Baldwin, basically nobody had recognized before. And he and Kuiper published papers and discovered more, and Bill and I also did that as well. Next. I introduced Bill Hartmann to both of his wives. That's my claim to fame. In this 1962 paper, Bill summarized what they had found out about basins, and that there were giant impact structures, what happened to craters when they got larger than a couple hundred kilometers. And they had multiple rings. You can see this is the illustration they published in their 1962 paper. I remember when that came out, I was working with them at that time. You have multiple concentric rings shown in red. There's the Nectaris one on the sort of right near the bottom side, and Imbrium is the top left, and Chrysium is on the right side in the middle. So there were these large crater basins, bigger than anything we'd ever considered to be a crater before. Multiple rings. The slopes on the inside of these rings were very steep. They were scarps. Faulting had occurred, and the slopes on the outer side were gentle, and they went away slowly. So they observed that. There were features that were radial, that were linear away from these round basins. The basins were depressed in the center. We didn't know how much then, but now with the GRAIL data, with the LOLA data that provides fantastic altimetry for the moon, we know now that the basins are typically a couple of kilometers below the surrounding level to 9 or 10 kilometers below, depending on which basin. So they're very much depressed in the center. They're flooded, many of them, the ones we saw on the near side of the moon, are flooded with dark material, which Ralph Baldwin had proposed was lava. And in that lava, there are these mare ridges, we called wrinkle ridges, and rills, which we'll see some a little bit from now. And these were concentric fractures. That's what they recognized, that the rills were concentric fractures around these depressed crater floors. And these things, unlike big impact craters, they had no central mountains. So the central mountains were replaced by a series of rings. And if you know the moon and you look at the top left of this image, there's the Imbrium Basin, the biggest basin on the near side of the moon. And on the right-hand side of that, you can see a white ringed crater called Archimedes. And Gene Shoemaker recognized that Archimedes wasn't formed immediately. It wasn't formed the same time the basin occurred. In fact, it was formed after the basin, obviously, since it's inside it. And the impact occurred and made a crater. But then lava flows, Mare Imbrium lava flows, came and surrounded Archimedes. So he was the first one to figure out there was an interval of time, which we now know was perhaps hundreds of millions of years in some cases, between when the basin formed and when subsequent mare lavas occurred. Next. Well, the sequence of morphology changes from small craters to basins is illustrated here. And by the way, there's a professional astronomer called Nemo who has online his illustrations, his PowerPoint illustrations for a class he teaches, a senior level, graduate level class on planetary astronomy. And it's an excellent class. And that's where I got this illustration from. The craters above a few hundred meters in diameter, up to about 15 kilometers in diameter, are simple bowl-shaped features. They could have been turned out on a lathe, one after another. In fact, the estimate is that there's more than 1 million craters on the moon that are a kilometer in size or larger. And of that million craters, probably 990 of them are small, simple craters like this. No central peak, no terrace walls. And then as you get to larger diameters, the 15 kilometers to a couple hundred kilometers, the hole that's made by the impact that came in and hit the surface of the moon excavated a large area, 2,000 kilometers apart across. And suddenly there were rocks all around that had nothing inside holding them up. And so they had large fractures all around a circle of the original transient cavity that was made by the impact, and terraces formed by the side walls moving in, collapsing inwards along faults that curved like that. And so the original diameter of the crater was increased by about 25% by this faulting that enlarged it. And as the shock wave progressed down through the target rocks, it basically rebounded up, the rocks rebounded up and made central peaks. So central peaks are from the deepest part of the target area where the crater was formed. Well, that's the way hundreds of craters are, thousands, until you get to about 300 kilometers diameter. And then there's two examples on the moon where there's a central mountain, a central peak, and it's surrounded by a peak ring like that. And Bill and I gave the name peak ring to that type of craters. And then after those two, the central mountain's gone forevermore in larger sizes. And so somehow the central peaks of craters are transmogrified, which is a wonderful word. It sort of suggests we don't know what's happening. And that was the case for many decades. The central peak somehow grows into a ring of mountains. And then at larger diameters, typically above 500 kilometers or so, the cavity in the ground is so large that there are more and more fractures as the ground slides down into the hole that's been made. And so those are the multi-ring basins. And that's the picture of Orientale, which is about 1,000 kilometers across. And we can just see the edge of it from Earth. Next. So as the energy increases from the impact, as the projectile size gets bigger, as the velocity gets bigger, the holes that are produced in the ground change their morphology. And really, there's just 3 or 4 morphologies: simple craters, complex craters like Copernicus, and then the transition to the multi-ring basins, the basins with the rings. So on this nice picture, and by the way, I originally put together some of these slides for a talk I gave in England. So you might notice that I have the photographer was typically somebody in England, or sometimes in the US, like Jim Phillips. There's a simple crater in the upper right. Simple craters are everywhere. They're bowl-shaped. They're not very interesting. But when you get the 100-kilometer wide crater like Copernicus, then you can see the individual terraces where separate faults cause the displaced rocks to slide down. And as they slid down, they met in the center, and they kept the crater from being much shallower than a simple crater is. A simple crater's depth is about 25% of its diameter. So Copernicus, though, depth is about 3%, 4% of its diameter. So large impact craters are much shallower for their depth, and they're full of stuff. And if you look at this picture of Copernicus, the bottom left quadrant is much smoother. Well, it turns out we finally found out, we used to think that was lava flows. We finally found out that smooth part is impact melt. The energy of the colliding projectile is so great that some rocks are just totally vaporized and melted. And some of them are splashed out beyond the crater rim, and others go straight up and come back down. And that's what happened to these. That's what produced these. So terraces, the central mountains, shallowness. And if you look all around the rim of Copernicus, there's a deep deposit of ejecta. The material that was previously inside is now outside, surrounding it. And as you go radially away, instead of being continuous ejecta, it becomes discontinuous. And you see some crater chains here at this place near Copernicus. And further away, the chains become more long, extensive, and greater spaces between craters, and you get bright rays. So we've all seen and love large, complex impact craters like that. I almost pushed the button for the next slide. Ken? Well, and then you jump up to Orientale, a big basin, about 1,000 kilometers wide. And as I said, as Bill Hartman said in 1962, no central peak, no terraces, deep, mare lavas in the center. And for the case of Orientale Basin, the ejecta scales up to be much larger than it was for any normal crater. And secondary craters we'll see, and the question is, are there rays? Do basins have rays that we can still detect? Next, Ken. Well, here's another illustration from Nemo, the guy who has this wonderful website. And the stages of crater formation, there's a couple of stages. First, there's the contact where the projectile hits it and it's destroyed. And the second is excavation. And third is what modification. So the impactor is destroyed. High velocity has caused shock waves to propagate downward into the target area of the moon and backwards through the back of the projectile. And the shock waves cause particles of the lunar surface to move up and down. As I say down there in the almost next to the bottom, they cause the excavation stage to occur and to instantaneously, within minutes, to remove gigatons of rock that had been firmly in place up until a few seconds earlier. The rims of impact craters, I don't know if you happen to notice, they're tilted up like that because the ground that was not directly impacted outside it, the surrounding of it, it responds by tilting upwards like that. And about half of the height of a rim of an impact crater or of an impact basin is due to the rebound of the surrounding ground. And the other half of the height is ejecta that falls back down on it. So the excavation stage happened in a few minutes, and then over a few hours is the modification. That's where the bigger holes, transient cavities that are produced by an impact, collapse, and concentric fractures form all around, and the rocks slide in, the flora gets elevated, and central peaks are produced. That's for impact craters. Next, Ken. The story is much more complex for basins, and we had 40 or 50 years where we really didn't understand completely what happens. Now, because of the ability to run massive computer codes that can mathematically explore how explosions occur, we have much better models that seem to fit what we observe. The top of this blue zone in the top picture is the transient cavity. That's the area that's been excavated by the impact. And the blue zone beyond the transient cavity, that's the area where the rocks have been compressed and pushed down. They've just been pushed down out of the way. And the green area is surrounding the impact melt that's totally melted or vaporized. And the green area is where the shock pressure was so high, all the mineral structures collapsed and were deformed, but it didn't melt. It wasn't high enough to melt. So apparently what happens is because the area of impact melt is so large on basins, it's not just large because basins are bigger than craters, it grows progressively larger in a percentage as you go from a small 100-kilometer wide crater to a 500-kilometer wide basin. That the green part comes up, is pushed up the sides and becomes the peak rings that we see on the insides of basins. The mantle has been pushed down, the crust has been pushed down into the mantle, it springs back up, and mantle rocks, molten mantle rocks, move up to near the surface. And when you hear about a mass con that Tony mentioned yesterday, mass anomalies, concentrations, it's because of the lava flows that are on the top of the basin after it's finally finished, and the uprise of the mantle, dense rocks. So there's more of this. As I say, it's very complex. We've just been finding out how it really works. Next. So each of these different processes that we saw on impact craters and in basins affects the surface. And what I want to get at in this talk is that impact basins make a large majority of all the surface features that you see. In fact, I'm thinking of writing another moon book that would be based on looking at the moon from the point of view of what did basins do to cause these landforms. So first thing is that when you have a projectile come and hitting the target, it erases, it just totally destroys whatever was there. And then the shock waves propagate through and it moves matter up and down. The high energy from the velocity of the impact causes the melting and vaporization I've mentioned. The hole is created, an ejecta, all the rocks that were previously in that part of the moon are thrown out. Some of it undoubtedly, for every time a basin formed, there would be meteorites of moon rocks falling on the Earth. Unfortunately, the last basin formed about 3.9 billion years ago, and it's really hard to find lunar rocks that are 3.9 billion years old. And so the crater collapses, as we said, expanding its diameter, creating scarps, this modification phase. So let's look at all these things that happen on basins. Ken? Well, first of all, there are lots and lots of basins. I made a catalog in 2004 of about 80 or so of them. Some of them were real, and again, Tony mentioned this yesterday, the catalog. Some of them were not real. And these are about the 35 or 40 most prominent basins. This is about half of the number that we think probably exist on the moon. And they're everywhere. So their effects are going to be everywhere. Next. And what happens for each of these basins, they totally erase what was previously there. So we have all these holes in the moon where the surface rocks down to depths of many kilometers are gone. Next. And where those rocks go is they get spread all over the place. Here in the center of this picture, and this is from a paper that just came out in March by some Chinese people named Liu. And again, Tony showed one of the pictures from their paper yesterday. That's a tremendous place to go to start, because in their supplementary material, they have a catalog of all the basins where they've measured probably 20 different characteristics for each basin. It's the most exhaustive basin catalog that exists. So Imbrium is in the middle. If you put your thumb and forefinger together on the picture, you've covered the Imbrium basin. But all these yellow lines that go way out, that's where the ejecta has been mapped to be. That's where we can see it today, 3.8 billion years later. It probably went further. So the previous picture showed where the terrain was totally destroyed. This shows where the terrain has been covered, buried. Next. And this is a picture that Tony showed yesterday. This is, if you look at the biggest, most likely to be real basins, and I think there are about 65, 70 here. That's the part of the moon covered by ejecta from the basins. And then next, if you add to that the lava flows that erupted in the floors of the basins, those are shown by the blue, much more than 50% of the total surface area of the moon is covered by basins and their debris and the lava flows that came up the fractures that they made. So almost any place we look on the moon, we're looking at some landscape that results from basins. And one of the other things that happens, you have an impact, especially an impact that makes a crater 1,000 kilometers across, you have massive moon-wide moonquakes. So everything that existed on the moon is going to be shaken immensely. So with the basin ejecta and lava flows, it's a lot more than 50%. But then when you include the seismic activity, every single piece of the lunar surface has been affected by basin formation. Next. Let's look at some of the ways in which the ejecta from the basin is displayed on the surface. The top left picture is the edge of Mare Orientale. And if you look at the crater near the top of that image that has a big shadow on it, that crater is Shaler, and it's 85 kilometers across. So you're looking at a big piece of the surface, and the main rim, the Cordillera rim of the Orientale Basin is underneath Shaler, and everything to the bottom right of that picture is the continuous ejecta from Orientale Basin, which was probably 3.8 billion years ago. And that ejecta is a couple kilometers thick. So you can see some of the craters there you can still recognize because they're only partly covered by ejecta, and others are completely covered. And if you look at the image on the bottom left, that's another place where there's ejecta, this time from the Imbrium Basin. And this is looking north of Mare Frigoris, north of Imbrium. And this is a place where there's lots of pre-existing pre-Imbrium craters that have had their walls destroyed. And what destroyed the walls was all this knobby, sort of rubbly material that fills those craters up. That's the type of ejecta that occurs and is in place further away when you're not right there on the very edge of the basin. And then the top right picture with all the green stuff, that is where ejecta has flowed across the surface, or it was ballistically impacted, and then it was still molten, and it flowed across the surface after ballistic deposition, and it filled the floors. And so if you look around Tycho on the near side of the moon, you can see all these flat floored craters that are very shallow. That's not lava flows. That was what we thought in the late 60s and early 70s. It's all basin ejecta. It's all stuff that's come out of Orientale and Imbrium and other bases, and probably ballistically emplaced, and then it was still hot and it just flowed. And the thing that shows up really well in this picture of the ejecta around Orientale at the top right is so much of it's filling the crater chains. So there are crater chains we saw around Copernicus, and there are crater chains around all the basins. And you can see that that ejecta goes about halfway around the circumference of the moon, of the moon. Next. And then here's another style of ejecta that's almost pasty. It flowed across the surface. You can see this surface I don't know if anybody knows the directions on the moon other than Tony and me, but it flowed across the surface to the southeast, and it just smoothed the surface. In some cases, it took jagged landscape of terraces and just smoothed them out like you had plaster putting on a wall and covering up the rough spots. So, and if you look at the top left corner, there's 3 or 4 overlapping craters that have had their common walls destroyed, and then they were later filled with lavas from the nearby lava flows. Those are secondary crater chains. If you look over the big crater in the bottom right, it's Julius Caesar, about, as it says, 85 kilometers wide. And above that, there's some other parts of crater chains. So large crater chains, 20, 30 kilometers across, exist around each of the basins. Next. And then the grooves. Imbrium is famous. It was discovered by Carl Gilbert in 1893. He noticed this. He was using the Naval Observatory telescope in Washington, D.C. He looked at the moon for 1 month, every night for the month, and he wrote an 1893 paper about the moon's surface and what caused features. That was probably the best paper for 50 or 60 years, but nobody read it. He was published in a journal that astronomers didn't read. Geologists didn't study the moon at all back then. So his paper was missed. But these long grooves and gashes that occur, that's where mountain-sized particles hit the moon surface at low angles and just cut their way through the surface. There's hundreds and hundreds of them all around Mare Imbrium. Next. And then ejecta. We talked about Copernicus, and every impact crater has ejecta. This is a piece of one of the Mare regions on the moon. Can anybody recognize what that Mare region is? I'll tell you. It's Mare Fecunditatis, and you can tell that because the 2 craters, small craters on the left side, the bottom half, have the railway parallel rays coming down, and the name of that just escaped me. Those are famous craters that everybody looks at the moon sees. Well, you can see their rays every single place covering this Mare, just a few spots that are still dark. So every place on the moon was covered by rays from impact craters, and the rays cover the highlands, but the highlands are made of a different type of rock. They're not dark minerals like the lava flows are. They're bright, and so we don't see the rays typically in the highlands. Next. So this is what crater rays look like, and this is what basin rays look like. Nobody knew this until 2008 using radar. Some people I know, here's Orientale Basin over on the left. They mapped the radar reflectivity, which depends upon the particle size. And there's an area that's smooth around the Orientale Basin on the left-hand side. And that's got heavy concentrations of ejecta. But then you can see smooth lines that radiate out almost on the bottom right, almost all the way across this image of the moon. And those are basin rays. Nobody had ever seen them before. So The impact basins are like the craters. They have the same set of features, but everything is exaggerated. Next. In crater chains, the picture on the left is a famous Apollo 15 picture, I think, of Copernicus crater at the top and one of its rays, and the rays are full of secondary craters. The middle picture is a secondary crater chain from Orientale Basin. And those craters, one after the other, are about 15 kilometers across. So those are secondary craters that are 15 kilometers across. The secondary craters for Copernicus are typically 1 to 3 or 4 kilometers across. Much bigger basin, much more energy, much larger secondary craters. And then the picture on the right is, I don't know, 1,500 kilometers away from Imbrium. And there's a whole cluster of craters. They're about the same size. They're about 20 kilometers across. This is on Mare Fecunditatis on the east side of the moon. Those are probably secondary craters too. Excuse me. It was some big mountain that was ejected from the formation of Imbrium, and it broke apart and hit in a cluster. If you look over at Copernicus on their rays, you can see clusters of small craters where the same thing happened. A piece of ejecta broke apart and landed in about the same area and made craters a couple of kilometers apart. Craters all over the moon that we used to think were impact craters that had been modified, they're almost certainly secondary craters from basins. Next. And then we noticed by looking at various craters on the moon and the experiments that NASA scientists did at Ames Research Laboratory near San Francisco, where they shot small projectiles down into targets at 15 kilometers a second impact as particles hit the moon. And when they made the particles come in at low angles, it turned out that the ejecta went downrange. The ejecta didn't spread uniformly in 360 degrees around. And in the area uprange is called a zone of avoidance. And it turns out that Tycho, here's a beautiful picture that a guy in Australia took. Most of these pictures that I've showed from people on Earth, they're all pictures that were donated, contributed to the Lunar Photo of the Day. So it's just wonderful to have so many. The zone of avoidance for Tycho is to the left. So the Tycho projectile came in at an angle, probably only about 15 degrees above horizontal, and it hit, and most of the ejecta went downrange to the right. And I suggest if we look at the picture we showed before of the ejecta from the Imbrium Basin, that's probably an oblique impact as well, because almost all the ejecta is to the right again, and you should point out, hey, don't pull a fast one on us. Look at all that lava flow from Oceanus Procellarum. There could well have been ejecta underneath there, buried. And you're absolutely right, there could have been, except when you look beyond the dark mare of Oceanus Procellarum, there's no ejecta there from Imbrium. So if you look how far the ejecta goes to the east, to the right, if it went the same distance to the left, we would detect some, and we don't. So there's been comments before that Imbrium may have been an oblique impact. Pete Schultz and some others believe that the Bay of Rainbows there, Sinus Iridum at the top left of Imbrium, may have been where the projectile first came in, a low angle projectile there. We're still investigating that. Next, please. And then the seismic shaking. Here's a beautiful picture of Tycho. This is a Lunar Reconnaissance Orbiter camera picture. And there's Tycho, a beautiful crater formed about 800 million years ago, which is the youngest big crater on the moon. And the terrace walls and the impact, the central peak and the impact melt on the floor, they're all in pristine condition. But if you look at almost all the craters around, their once sharp rims have been rounded down. They're not deep anymore. They've been filled in with something. So seismic shaking and ejecta from impact basins, and definitely seismic shaking for these craters that are near Tycho from when Tycho formed, and ejecta from Tycho, goes to modify and degrade every crater on the moon. And the older the crater is, the longer the time it's had to be degraded. And I say seismic, shaking and ejecta from basins, but also every crater, like I said from Tycho, every crater causes moonquakes that causes material to move down slope. Next. And the other thing that happens when there's a crater formed or a basin formed is that the rocks are fractured. The rocks near the surface are excavated and melted and whatnot, but the rocks below that are deeply fractured. And Bill Hartman back in the 60s realized that there were so many old craters and basins that the lunar crust that going down kilometers, multiple kilometers, was probably seriously fractured. And there would be a megaregolith. And a megaregolith is a zone that's broken up, rocks broken up and made to pieces and moved around. And above that, we now know, well, we found out a long time ago in Apollo period that there's a regolith. The regolith is not as mega. The regolith is just a few tens of meters thick on the Mare and maybe 100 meters thick in the highlands. That's the dust that forms. That's the stuff that comes into the spacecraft when the astronauts come in out being outside. When you see footprints, or when John Young was testing a lunar rover and there was a rooster tail of dust, that's all bits of the regolith that are thrown up. That's a real hazard for being on the moon. It can send everywhere. Next. And then let's look at the basins themselves and the structures that form. So to the left is Imbrium Basin, and that's one of Maurice Collins's visualizations of the topography data from Lunar Reconnaissance Orbiter. And Maurice is, I think, on the YouTube video. So hi, Maurice. He and I have worked together. We published a Moon Atlas in 2013, and we're working on more things now. So you can see there from on the left-hand side, there's the main Apennine rim of the Imbrium Basin, and inside that there's a rim of wrinkle ridges. And if you look at the bottom here along the edge of Mare Frigoris, there's the curvature of the edge of ejecta looks like another ring there. And then Orientale, you can clearly see three different rings, the big one, the Cordilleras, and then the outer Rook and the inner Rook. So basins make these complex structures that I've been describing before, and they're beautiful pictures right here. Next. And then the basins create these giant fault scarps that go down that allow the terraces, the mega terraces, to slide down on the basins. And you can tell those basins are faults because if you look at the right-hand image of a close-up of Orientale, you can see that those young lava flows, dark lava flows, are coming out right at the edge of those fault zones, the fault scarps. So the places where lava could reach the surface is where the faults go down deep to interact with where magma is. And that happens in the center where there's intense brecciation, fracturing, and it happens on the edges. And then K.C. Powell, who's just this amazing photographer who takes pictures with his 10-inch reflector from his balcony in Hong Kong. And he only has a small piece of the sky available that he makes these magnificent photos in. He's the first, I think the first one amateur to take photographs of these young lava flows on the moon, on Mare Imbrium. And when we say young, most of them are still around 3.5 to 2.5 billion years old. Some of them may be as young as 2 billion years. So they haven't been beaten down, the edges haven't been eroded away by small scale impacts. And so you can still see the flow edges of this large lava flow. Next. And then another thing that happens to basins is the lava is erupted, the Mare lava is erupted on the surface tens to a few 100 million years after the basin formed. It comes from down below It erupts through fractures onto the surface and makes a pile of lava that's anywhere from 2 to maybe 5 kilometers thick. That's a heavy weight, and it solidifies, and that heavy weight pushes down on the basin floor, pushes the basin floor down, and the lava, the solidified lava that used to be in a space maybe 500 kilometers wide, as it goes down, it has to occupy a lesser diameter, maybe 400 kilometers. So inside, where the lava fractures so it could be a smaller space, one piece of the solid lava flow goes under it, a low angle fault, and that produces the wrinkle ridges. We used to think, Bill Hartman and I published in '71, that the wrinkle ridges could be faults and they could be lava flows. We haven't seen a lava flow come out of a wrinkle ridge anywhere. Even the lava flows I showed you before, it didn't come from the wrinkle ridge. And then if you look at this wonderful picture that Stefan Lamel sent from England 10 years ago, on the right-hand side of it, you see this parallel fractures, rills, concentric rills. And that's where, when the basin subsided, the solid lava flow had to move fast, and it had to bend, and it fractured. Let's go to the next one now. And here's a map from LRO of all the lunar surface except the polar regions, and the dark lavas show up very well. And what you see is that almost all the lava flows occur on the near side of the moon. The center 2/3 of this image is the near side, and the 1/4 piece on both right and left edges, that's the far side. The far side has at the top right Moscoviense, Mare Moscoviense, the Sea of Moscow, and on the left side, just near the near side, is Orientale. Those are the two largest lava flows on the far side. There are some more inside the South Pole Aitken Basin. That's a basin that's the largest one on the moon, about 2,500 kilometers across. And if you look at the bottom left corner, you can see about 1/4 of it. In the bottom right corner, you see another less than 1/4. And so we say the impact basins on the near side are wet. They're full of lava. They're full of Mare lava flows. And most of the impact basins on the far side are not. They're dry. What's the difference? Well, there's two reasons. Next. This is a map also from the Lunar Reconnaissance Orbiter of the crustal thickness, and Tony showed a map like this yesterday. And the red and the white are the thick parts of the crust, 40 to 50 kilometers thick. And the green, and especially the blue, are the thin crust. And if you look over and, well, I don't know, if you count the number of blue circles from the right side, there's 1, 2, 3, 4. The fourth one is Mare Crisium. Mare Crisium is this beautiful basin. We see it has very few impact craters on it. The crust under Mare Crisium is only 5 kilometers deep. You know, you could drill a hole through to the mantle of the moon there. So the near side of the moon has a very shallow, thin crust. The far side of the crust is 2 to 10 times as thick. And so even if there was the same quantity of magma below the surface, it would have to penetrate through a much thicker crust on the far side. And next. And this is just when the lava flows erupt. We landed on Apollo 11, 12, 14, 15, and 17 on lava flows. And so we have samples of the ages of 5 lava flows on the moon. And the Russians landed in Crisium. So we got their couple samples. And then just recently, the Chinese landed, and we got a 2 billion-year-old age for lava flows near Aristarchus. But if you look at the histogram at the bottom right here, you see almost all the lava flows whose ages we determined by counting in number of impact craters per unit area on them, calibrated by the lava flows we've actually brought back and dated. almost all the lunar volcanic activity was been between about 3.8 billion years and 3.3 billion years. And then it dribbled out to 2 billion years. We now have a firm date from the Chinese samples. And from crater counting, we think very small amounts of lava flows 1 billion years ago. So the heat engine that drove melting of the lunar interior mostly turned off by about 2.5 billion years ago, except in a few places it continued. And that's a real question now. Why? What caused it to continue? Next. So when did the basins form? 88, 40, whatever the number of basins is, they all formed before 3.8 billion years ago. And here's sort of a chronological sequence from the oldest to the youngest for some of the basins you know. The South Pole Aitken is the oldest one. And then Fecunditatis, I've mentioned, Nubium, Smithy, those are all old basins. Nectaris is middle age, Serenitatis is younger, but it's been in a bad position. It's been right next to Mare Imbrium. And when the Imbrium basin formed, it really very instantaneously degraded what's left of Serenitatis. Humorum, we saw some pictures of, Chrysium, Imbrium, those are all the young ones. And then Imbrium and Orientale 3.8 about. So that's when all the big action, all the major changes in lunar history that affected the surface we see today happened then. Next. So if all the basins formed by 3.8, we can't blame the basins for anything that happened after that. Anything has an asterisk with it. All the impact craters like Tycho and Copernicus and almost any other impact crater that's got rays, that looks fresh, the basins did not influence them at all. But the lava flows that are younger than the basins, like this new 2 billion year old one and others, all those lava flows only reach the surface of the moon because the basins that were formed maybe 1 billion or 2 billion years before then, those basins made the fractures that provided the conduit for lava to reach the surface. This is a picture about 200 kilometers across here of the center part of Mare Nectaris. And there's one crater, Ross, down here, that's, I think, as I recall, 6 or 7 kilometers wide. And almost all the other craters on there are secondary craters from Theophilus. So for the last 3.9 billion years, that's how old the lava flows are there. There have been almost no craters formed. The rate of crater formation was 1,000 times higher in the first 500 million years of the moon's history than it was any time since then. So almost everything we see on the moon formed ancient at the time the basins did. Next. Now, an explanation that's just come out, it was just published in spring of this year, talks about how the formation of SPA, the South Pole Aitken Basin, how it totally reorganized the way the moon works as a world. And this is one of Maurice Collins in New Zealand, another one of his images where he took the topography data from the Lunar Reconnaissance Orbiter and visualized it and put colors on. So you can see up at the top is yellow and red, thick crust. Down at the bottom is on the near side, and you can see some bluer crust there. In the basin itself, 9 kilometers deep, is the biggest low spot on the far side of the moon. Next. The exciting thing that came out just a couple months ago is that there's this big asymmetry on the near side and the front side. The near side, the image on the left in the center there, the blue image shows how much thorium there is. Thorium is sort of a tracer for other important rare radioactive materials on the moon. The yellow and the red are where thorium is the most intense on the moon, and that's where Mare Imbrium is. That's where Humorum is. So the moon has most of its volcanism right there where there's an excess of radioactive elements. They provided heating that the rest of the moon, if you look at the far side of the moon, the rest of the moon has a very low amount of thorium. There just wasn't the same amount of heating of the crust of the moon on the near side and the far side. So the paper that just came out has more of these mathematical models. And if you look at the diagram on the right-hand side, there's a black dot coming in at the top of each one of these. There's a step through of them. And that's a projectile hitting to form the South Pole Aitken Basin. And the gray series of illustrations is just the general interior of the moon, and the purple edge to it is the surface part of the moon that presumably when the moon formed and totally melted, this layer that we call the creep, that's what the layer is on the left side with the yellow and the red, this radioactive rich stuff. We believe that was concentrated all around the moon, but the impact that caused this largest basin on the moon caused that surface layer to move all around the moon in every direction to flee away from the energy of that impact. And it concentrated and froze and formed the crust of the near side of the moon, and in particular where the yellow and the red is. And the series of 4 circles on the right, that shows how the heat was transported through the moon, and the whole moon warmed up from that. And that warming of the entire moon, according to this brand new theory, allowed this radioactive rich crustal layer to concentrate on the other side. So this is brand new. We've known about the concentration of radioactive elements. We've known about them for 20 years, but nobody had an explanation. So here's a new explanation, which may or may not be right, but it accounts for lots of neat things. Next. All right, what can we thank basins for? First of all, the near side of the moon, which has all these basins with lava flow in it, is intensely more interesting than the far side of the moon. And if you look at the 2 diagrams at the bottom is a full view of the far side of the moon, and there's almost no lava flow, and it's nothing but impact craters. It's nothing but craters on tops of craters on tops of craters. And I love craters, but my God, they're boring when there's nothing else. And on the left side, we have a picture of Archimedes, and it's got lava flows inside it that come up fractures. It's surrounded by lava flows. There's mountains there. There's a variety of ways in which impacting has interacted with lava. So the South Pole Aitken Basin concentrated all this radioactive material on the near side of the moon. So we have all these beautiful lava flows with the wrinkle ridges that Alberto was looking at, the mountain ranges when the basins formed that threw up the Apennine Mountains and the Altai Mountains, forming these beautiful, the largest mountain ranges on the moon. Fractures the crust so that lava could reach the surface. So we have impact basins, and in particular, the biggest one to thank for making the moon the most fascinating object in the night sky. I think that's the last slide, isn't it? Well, the moon will never be the same, I hope, after what you've heard today. In the next slide, keep observing. And this picture up there is from Maurice again. So he and I are partners on our research. So I thank Maurice for a number of these slides. I'll be happy to take any questions if anybody's still awake.
No, you've done good.
I don't know. Every time I see those crater chains, I get really excited about that. You know, imagining what that event looked like as it happened. You know, so
you wouldn't want to be anywhere nearby.
No, but
probably even on Earth, you're likely to get hit by debris.
It would be incredible. Really, it's just amazing.
Why are some things arbitrarily called ocean of, and others are called sea of?
Yeah, Procellarum is the largest smooth area on the moon, and so when in the 1600s, when people were mapping the moon for the first time and assigning names, some of them thought Galileo knew it wasn't true, but other ones who followed him thought that those were oceans, and so they named the smaller ones the ones that were contained seas, and there was this one big thing that wasn't readily contained in mountains, and they called that an ocean.
Okay. By the way, I can speak from experience in, you mentioned at the beginning of your talk, a book called Epic Moon.
Yep.
And I have that. And, you know, it's kind of a fast read. And it's so interesting to see the history of the beginning of mapping of the moon in that book.
Yeah.
I highly recommend it.
I agree. Bill Sheehan and, oh gosh, who's the co-author? I know him. I can't remember, but yeah, it's an excellent book. And then Ewan Whitaker's book, Mapping and Naming the Moon, is excellent also to go over that history.
Chuck, in defense of small stuff, I've been teaching people that to image smaller and smaller for the simple reason that there's at least 3 out of 5 nations that are going back to the moon that intend to stay, and they're going to start digging holes.
Yeah.
And in processing materials, and if you want to see that, you've got to hone your skills for seeing the small stuff now. And that's the defense I have for imaging small things.
I totally agree with you. When I said for a long time observers overlooked the big stuff, the most important stuff, we didn't pay attention to it, we didn't see it. But that doesn't mean we should neglect everything else. The photographs that so many people are taking, amateurs are taking of the moon now, sometimes you can't tell if they're, you know, taken by a spacecraft or if they're taken by somebody on the Earth with an 8-inch or a 12-inch telescope. It's just marvelous.
It's like the images of planets. The images of planets that are coming out of amateurs now are equivalent to the pioneer images.
And better, I would say, yeah.
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 Right.
I have a question about mascons.
Uh-huh.
Okay. Used to be that the astronauts would talk about passing over mascons and they would feel the gravitational effect of the mascon where they were going around the moon. And it was attributed to iron nickel asteroids that were buried in that, or that was that mascon. So if that's not true, what is that? Basalt or?
It's basalt, yeah.
Okay.
It's the asteroids that came in and hit and made these big basins. They were totally destroyed, and fragments of them, pieces of them were scattered everywhere. So there's not a concentration of them anywhere that would cause that sort of mascon. The mascons that, again, we have models, and variety of teams make different models, and after a while they all seem to converge on the same explanations. We're pretty sure now it's the lava flows that are on the surface. You know, if you have a 4-kilometer thickness of lava flow that's right on the surface, if the spacecraft's flying 50 kilometers above it, that's a large gravitational attraction compared to the low density rocks outside of that. And then also, that's not enough to explain the mascon. We think from the cratering theories and the diagram I showed you and whatnot, that the mantle rose up underneath these basins. And now with the Grail spacecraft that mapped the gravity fields of the moon, we can beautifully see where the mascons are well defined inside basins. And it's the inner ring of Mare ridges, which shows you exactly where the mascon rose up, and that defines the transient cavity, the initial hole that was made by the impact. We've learned so much about the moon in the last 10 years, longer than that, starting with Kaguya, the Japanese spacecraft, and then the Lunar Reconnaissance Orbiter. We used to think we knew so much, and we did compared to people a generation before, but now we've learned so much more. It's overwhelming, but I love it.
Well, all this stuff that happened to the moon happened to the proto-Earth too.
Yep.
And so what does that say about what we know about the Earth?
Well, I like to say that that the moon is the Smithsonian institution of the solar system. we have the Earth, which is this big dynamic planet. The average age of the surface of the Earth is 500 million years. because the 70% of the Earth is covered by ocean floors whose average age is something like 150 million years. So you take all of the 70% ocean floors that are young and the 30% of continents that only in rare places did they go back 3.9 billion years, even though we existed before then, those rocks have been destroyed. Our average age is 500,000 years, which incidentally is the average age of Venus, and it's the average age of Titan, satellite's moon Titan.
Wow.
So the moon preserves its history. We talk about a almost a billion year crater like Tycho as being young. That's 100 million years is young. Copernicus is a billion, that's young. We have 3.9 billion year old rocks everywhere in the moon. So the moon tells us what, just as you said, Rick, the moon tells us what the Earth must have gone through, but that's all been erased by plate tectonics on the Earth. It's all been erased by ocean formation and destruction.
Weather. And weather.
Yeah, and weather. We need both.
And,
Yeah.
a question related to that, since the early bombardment 3.8 billion years ago, have there been periodic multiple impacts as the moon and the Earth system goes around the galaxy?
Yeah, there's been discussions of that, not so much based on the moon data because we don't have enough ages for the craters, but that's one of the things that has been listed as a goal for when we go back to the moon and we have people on the moon collecting lots of samples. Can we tell where the solar system went through the ring plane of the galaxies every 250 million years? On the Earth, there's some evidence on clumping of ages of impact craters, but we don't have enough impact craters to have a very statistically reliable sample. And it's interesting, the Chicxulub impact 65 million years ago, that was really, really young.
Yes,
that made a crater on the Earth 100, 120 kilometers wide, something like that.
Right.
No crater on the moon in the last 65 million years has been made anywhere near that size. So there are these random, rare events that are big.
Right.
Okay, I'm going to interject here. I think Tim and we're going to get going here.
Oh yeah, you got to give away prizes. That's why people
stay. Prizes. But I want to. There's your Atlas to the Moon from John Nagel there. I would like to also mention, if you really want a simple theory of what's going on the moon, and this is meant in jest. I like science fiction. Most science fiction isn't that great, but there is a great movie that came out that's got great special effects, and I don't know if it's plausible, but you can stream it. It's called Moonfall. So check it out. And even if it's not necessarily so, it's a good movie. Moonfall.